In the vast darkness of the cosmos, stars are born with promises of brilliance, burning their fuel in dazzling displays of light that reach across unimaginable distances. Yet, even the mightiest of stars cannot burn forever. They live fast, they shine bright, and they die in violence. Among them are the giants, stars many times more massive than our sun, their fates written the moment they ignite in nuclear fire. These titans spend their lives in a furious struggle against gravity, forging heavier and heavier elements in their cores until their fuel runs out. What follows is a finale so violent that it shakes entire galaxies. It is the spectacle we know as a supernova, a death scream that radiates more energy in mere seconds than our sun will in its entire lifetime. When such a star collapses under its own weight, the outer layers are hurled into space, enriching the universe with the raw materials for planets and life. But what remains behind is far stranger. The core, once the powerhouse of the star, shrinks down under the unbearable pressure of gravity. The atoms inside are crushed, protons and electrons forced together to create neutrons. In this transformation, the core becomes something new, something neither ordinary matter nor pure energy, but a neutron star. Imagine the mass of our sun, but confined within a sphere no wider than a city. This is no poetic exaggeration. It is a fact of physics. A neutron star is an object born at the very edge of survival, teetering between existence and annihilation. Gravity pulls inward with unrelenting force, determined to crush the core further, while the quantum rules of matter push outward with equal determination. This is not a fight waged by ordinary pressure, like the air in a balloon pushing against its surface. It is a deeper resistance, something known as neutron degeneracy pressure. At the heart of quantum mechanics lies the rule that identical particles cannot occupy the same state at the same time. Neutrons are packed so tightly together that this rule itself becomes the only wall holding gravity at bay. But this wall is not impenetrable. It is not a permanent defense. It is, instead, a delicate balance that defines the very existence of a neutron star. The star does not know peace. It exists in an eternal stalemate between collapse and survival, a cosmic tightrope stretched across the abyss. For the moment, the neutrons win, and the star endures. Yet always looming is the question of limits. How strong can this pressure remain? How much mass can the star bear before the rules of quantum mechanics themselves surrender to gravity? We speak of neutron stars as if they are survivors, but in truth, they are more like fugitives. They flee from the inevitable collapse that awaits them should their mass grow beyond a hidden threshold. This threshold is unknown in precise value, but it is believed to lie between 2 and 3 times the mass of our Sunday. Below that, a neutron star holds the line, its particles refusing to give way. Above that, the balance fails, and the object falls inward towards something darker, something no force in the universe can resist. This is the razor's edge on which a neutron star lives. Born from destruction, they are remnants of firestorms, husks of titanic suns. Yet in their silence, they hide one of nature's most fragile balances. To watch them is to see survival itself stretched to its absolute limit. And so we arrive at the haunting question: what if gravity grows stronger than this balance? What happens when the universe itself demands that even neutrons can no longer hold their ground? The answer leads us to places where matter dissolves, where the fabric of space and time folds inward, and where light itself is trapped in an eternal fall. It is here, at the end of survival, that we step into the shadow of the black hole. The collapse of a giant star into a neutron star is not the end of the story. It is only the beginning of a strange new existence. Imagine an object only a few tens of kilometers across, smaller than a city, yet carrying the weight of the sun itself. Its density is so immense that a single teaspoon of its matter would outweigh entire mountains, billions of tons in a tiny pinch. This is a neutron star, an object balanced on the knife edge of physics. Inside this stellar remnant, atoms as we know them no longer exist. The pressure of collapse has pushed electrons into protons, leaving behind a sea of neutrons pressed shoulder to shoulder, each one refusing to give up its place. This resistance is what physicists call degeneracy pressure, born not from heat or motion, but from the quantum rule that no two identical particles can occupy the same state at once. In the silence of a neutron star, this invisible law of nature becomes the last shield against gravity's relentless pull. To understand the scale of this balance, picture gravity as an unending tide. On Earth, it keeps our feet planted on the ground. In a neutron star, gravity is so ferocious that even light struggles to escape its pull, though not quite to the level of a black hole. Every neutron within its core is locked in a desperate struggle, packed so tightly that the star itself becomes one colossal atomic nucleus. The surface is no gentle crust, but a sheet of matter harder than steel, while beneath lies a fluid ocean of neutrons, flowing with unimaginable density. The star is held together by the very laws of physics that forbid particles from being identical in every way, and for the moment, this suffices. Yet, it is not invincible. Just as there is a limit to the weight a bridge can bear before it collapses, there is a limit to how much mass a neutron star can hold. Add too much matter, and the degeneracy pressure falters. The neutrons, already squeezed to their limit, cannot resist the growing force. If the mass grows too great, the balance shifts. The star trembles on the brink of a new collapse, one with no return. The thought is unsettling. Here is an object already pushed beyond comprehension, already stripped of familiar forms of matter, and still, it is not enough to silence gravity. Instead, gravity waits patiently, like a predator. A neutron star can hold on for millions, even billions of years, spinning in the darkness, shining faintly in X-rays or radio pulses. But it is always only one step away from catastrophe. If it gains more mass, perhaps by pulling material from a companion star or colliding with another neutron star, the fragile equilibrium shatters, the shield of degeneracy pressure collapses, and gravity takes its final victory. This is the precarious existence of neutron stars. They are survivors, yes, but not conquerors. They are guardians of a balance written in the smallest rules of the quantum world, yet their lives are overshadowed by the ever-present threat of collapse. For all their endurance, they are not eternal. There is a weight they cannot bear, a line that cannot be crossed. The moment they approach that line, the moment their mass grows too great, their story changes forever. And so the question remains, what is this limit? At what precise point does a neutron star cease to be a star at all, and instead fall into darkness? The answer lies in the Tolman-Oppenheimer-Volkoff limit, a boundary in physics that divides survival from surrender. To step closer to this limit is to see how gravity, patient and unyielding, always waits for its inevitable triumph. The balance that allows a neutron star to exist is so extreme that it almost feels unnatural. Yet it is entirely real, and across our galaxy, hundreds of millions of such stars drift in silence, each one a relic of a catastrophic death, each one perched at the threshold between survival and collapse. They are often invisible to ordinary eyes, detectable only through their pulses of radiation or their influence on nearby companions. Still, when we study them, they tell us something profound about nature itself. They reveal the lengths to which the laws of physics will stretch to resist gravity, and they show us the exact point where those laws begin to fail. To look at a neutron star is to look at resistance embodied. Think of it as the final cry of matter refusing to surrender, the last outpost before gravity devours everything. These stars are not simply leftovers from supernova explosions. They are laboratories written across the universe, places where matter is pushed beyond anything we can recreate on Earth. Inside them, Neutrons move in strange states, quantum fluids that defy normal intuition, sometimes forming superfluids that flow without friction, sometimes forming superconductors that channel magnetic fields with impossible strength. The surface fields of neutron stars can be trillions of times stronger than the magnetic field of Earth. This is not simply survival. It is survival at the edge of what is possible. But even in their strength, there is fragility. The more massive the neutron star, the more precarious its balance becomes. The degeneracy pressure that holds the neutrons apart is like the final pillar holding up a collapsing temple. It is strong, but it is not infinite. As the mass creeps closer to the hidden threshold, gravity bends space more severely, curves time more violently, and pulls with an intensity that nothing can resist forever. At this threshold, neutrons themselves begin to falter. Their structure, once indivisible, may dissolve into something even stranger, perhaps quark matter, perhaps states we have yet to name. The neutron star's identity unravels, piece by piece, until gravity takes it entirely. In these stars we see a cosmic lesson. Survival is not eternal, balance is not permanent, and even the most stubborn of matter can only resist for so long. The neutron star lives for millions of years as a survivor, but in truth it is only postponing the inevitable. One day, by accreting matter, or by merging with another remnant, it will cross the final line. And when that line is crossed, there is no return. The object does not simply change form, it undergoes a transformation that removes it from the visible universe. Light itself can no longer escape. We stand at the edge of that idea, and it is both awe-inspiring and terrifying. Neutron stars are windows into a deeper truth. They remind us that gravity is not merely a gentle force pulling apples to the ground or keeping planets in orbit. Gravity is the one true architect of cosmic fate. It can build stars and tear them apart. It can scatter the elements that make life possible, and it can swallow entire suns into nothingness. In neutron stars, we see gravity at its most cunning. It allows them to endure, but it also waits, biding its time, ready to pull them into darkness when their weight becomes too great. This chapter closes with a haunting vision. The death of massive stars gives birth to survivors that should not exist, yet they do, suspended in an impossible balance. They are monuments to the power of physics, and at the same time, they are omens of collapse. For in the silence of their neutron-packed hearts, the story is already written. Survival cannot last forever. The next step in their journey is the most mysterious transformation in the universe. What if gravity grows stronger than the pressure of neutrons? What if the balance is lost? Then the neutron star will vanish, replaced by something darker, something more mysterious, something that marks the end of matter and the beginning of a singularity. This is where our story now turns, into the realm of limits, into the threshold discovered by the pioneers of relativistic physics. It is here that the line between neutron star and black hole is drawn, sharp and absolute. It is here that gravity finally shows us that survival itself has boundaries. They are smaller than a city, yet they hold the weight of the Sunday. To stand on the surface of such an object would be impossible, for the gravity would crush you in less than a heartbeat. A neutron star is the very definition of survival pushed to the absolute edge. Imagine taking all the matter of our sun and packing it into a sphere barely 20 kilometers across. What you create is not merely dense, but unthinkably so. A teaspoon of that matter would weigh billions of tons. Mountains would be like dust compared to it, and steel would bend like paper. These objects are born in fire, yet they live in silence. When a massive star explodes as a supernova, the outer layers are cast into space, but the inner core collapses. What is left behind is a neutron star, a remnant that exists in defiance of gravity itself. The pressure holding it up is not the same as in ordinary stars. In a main sequence star like our Sun, nuclear fusion pushes outward, balancing the inward pull of gravity. In a white dwarf, electron degeneracy pressure performs this role, a quantum resistance that prevents electrons from being squeezed into identical states. But in a neutron star, even that is not enough. Gravity pushes so hard that electrons and protons merge, creating neutrons. The balance then relies on neutron degeneracy pressure, a final stand by matter itself. This pressure is not intuitive. It is not the kind of pressure you feel when you inflate a balloon. It comes from the strange rules of quantum mechanics. Neutrons are fermions, which means they obey the exclusion principle. They cannot occupy the same quantum state. When packed together, they resist further compression, not because of physical contact, but because the laws of nature forbid it. This invisible barrier is the only thing preventing a neutron star from collapsing all the way down into a black hole. Even so, the gravity of a neutron star is overwhelming. Its surface gravity is about 200 billion times stronger than Earth's. If you dropped a pebble, it would hit the surface in less than a millisecond, releasing as much energy as an atomic bomb. Space itself bends dramatically near such an object. Light traveling past it curves, time slows, and the star becomes a distorted lens on the fabric of reality. The rules we take for granted on Earth falter in the presence of such immense gravity. Neutron stars are not uniform inside. Beneath their crust of crystalline nuclei lies an ocean of neutrons flowing like a quantum liquid, sometimes forming a superfluid with no resistance. In the depths, exotic states of matter may exist, phases that we cannot recreate in laboratories. The magnetic fields of neutron stars are equally extreme. Some, known as magnetars, have fields 1 trillion times stronger than Earth's, powerful enough to tear electrons from atoms and reshape entire regions of space. The very existence of such objects stretches imagination to the breaking point. Yet for all their exotic features, neutron stars are fragile in one crucial way. Their balance depends entirely on their mass. Add more matter, and the star grows more unstable. Push it far enough, and the neutron degeneracy pressure can no longer hold back the crushing weight. It is like a climber hanging from a cliff edge. For a time, the grip holds, the fingers lock tightly, but gravity is relentless. Add just a little more strain, and the grip fails. The fall begins. This makes neutron stars some of the most precarious objects in the cosmos. They can spin hundreds of times per second, beam radiation like cosmic lighthouses, and survive for billions of years. Yet the addition of just 1 or 2 more suns worth of mass can decide their fate. At that moment, the balance breaks, and the star begins the irreversible journey into a black hole. For now, they remain. They endure in their strange quantum states, their immense gravity and impossible density, defying our everyday logic. But survival has limits, and neutron stars live in constant proximity to the boundary between existence and collapse. That boundary is given a name, a theoretical threshold defined by physics itself. The Tolman-Oppenheimer-Volkoff limit marks the point where degeneracy pressure fails and gravity claims its ultimate prize. The very existence of a neutron star invites us to question how matter behaves when pushed beyond all ordinary conditions. On Earth, we are used to matter as a collection of atoms, with electrons circling nuclei and chemical bonds defining the world around us. In a neutron star, that familiar order is gone. Atoms cannot survive such pressure. Electrons are forced into protons, and the ordinary structure of matter collapses into a single, uniform sea of neutrons. It is as if the entire star has become one gigantic atomic nucleus, a sphere of matter stripped of individuality. From the outside, it appears deceptively simple. A dark, compact sphere, only a few tens of kilometers across. But inside, nature writes in layers. The crust is a lattice of nuclei, a crystalline surface harder than anything we know, capable of holding mountain-like ridges only millimeters tall, because gravity flattens everything so strongly. Below that crust lies an ocean of neutrons, flowing as a superfluid with zero viscosity. This is not just speculation. Pulsar glitches, sudden changes in rotation rate, hint at the existence of this hidden superfluid interior, as if the star's core is whispering secrets to us across the void. Deeper still, Beyond the neutron ocean, the matter may exist in states no laboratory can reproduce. Protons and neutrons might dissolve into their constituent quarks, creating a strange soup of fundamental particles. Or hyperons, particles containing heavier quarks, may form. These possibilities remain uncertain, but they point to a deeper truth. A neutron star is not just a stellar remnant. It is a place where the known laws of physics are stretched so far that they begin to blur into speculation. And yet, despite this strangeness, the star holds together. Neutron, degeneracy pressure, is the guardian, the invisible force that prevents total collapse. It is a silent standoff between gravity, which demands that everything fall inward, and quantum mechanics, which refuses to let identical particles overlap completely. For now, quantum rules prevail. The star remains intact, spinning in the dark, sometimes sending radio pulses across space, sometimes glowing in X-rays. It is a survivor, but a fragile one. What makes this fragility so haunting is the precision of its balance. Unlike ordinary stars, which can shed mass or adjust their fusion rates, a neutron star has no such options. It is a rigid equilibrium, and the moment its mass exceeds a certain threshold, the balance breaks. There is no gradual adjustment, no second chance. Gravity seizes victory instantly. The neutrons are overwhelmed, and the collapse begins. To put this in perspective, consider the difference between a neutron star and a black hole. A neutron star has a surface. If you could somehow survive the gravity, you could stand upon it. A black hole has no surface, only an event horizon from which nothing returns. The transition between the two happens the moment degeneracy pressure fails. The neutron star has no warning, no slow transformation. It simply crosses a line written into the equations of relativity and quantum mechanics. And in that instant, it becomes something else entirely. Astronomers have spent decades searching for the precise value of this line. We know it exists, but its exact placement remains elusive. Observations of the heaviest neutron stars, those close to 2 solar masses, suggest the threshold lies not much higher. Perhaps 2.5 solar masses, perhaps 3. Beyond that, there is no hope of stability. Even neutrons cannot resist. The star falls inward, crushed into a singularity, hidden behind an event horizon. It is sobering to realize how small the gap island. A neutron star, barely heavier than 2 suns, may survive, while one just a little heavier becomes a black hole. The difference between survival and collapse is measured not in orders of magnitude, but in the addition of a single solar mass. This razor-thin margin defines the destiny of stars, and it is here that the drama of survival becomes most intense. This brings us closer to the Tolman-Oppenheimer-Volkoff limit, the theoretical maximum mass a neutron star can sustain. This limit is the frontier where gravity meets its only rival, quantum degeneracy pressure, and wins. To approach it is to approach the end of survival, the point where even the strangest states of matter cannot resist collapse. The neutron star, in its silence and immensity, embodies the fragile balance between 2 titanic forces. On one side, gravity pulls with relentless persistence, demanding collapse. On the other, quantum rules push back, declaring that neutrons cannot all occupy the same state. The star exists only because of this standstill, but the standstill is temporary. The neutron star is not a permanent citizen of the cosmos. It is a temporary monument, a reminder that survival has boundaries. Astronomers who study these stars are always searching for the heaviest among them. Each discovery pushes closer to the breaking point. When we find a neutron star with nearly twice the mass of the Sun, we marvel at its defiance. When we find one even heavier, nearly 2.5 times the mass of the Sun, we begin to see the shadow of collapse waiting in the wings. No neutron star has yet been found above 3 times the mass of the Sunday. That silence is telling. It suggests that the laws of physics themselves forbid such a star from existing. It suggests that above this invisible boundary, The only outcome is a black hole. This is the last stand before collapse. Neutron stars are not simply remnants. They are thresholds. They are objects that show us how close matter can come to the edge without falling over. They are the bridge between the visible universe and the invisible, the final form of matter before gravity swallows it completely. In their presence, we see how finely tuned survival can be, how delicate the balance is between existence and annihilation. The Tolman-Oppenheimer-Volkoff equations, derived from Einstein's general relativity, describe this limit. They tell us that above a certain mass, no solution exists for a stable neutron star. In other words, the equations themselves give up. They no longer describe a star, they describe collapse. This is not speculation. It is written into the very mathematics of space-time. When the weight is too great, gravity is not resisted, it is absolute. The importance of this limit cannot be overstated. It is the dividing line between stars and singularities, between survival and surrender. Below it, we find pulsars, magnetars, spinning remnants that continue to shine in their strange ways. Above it, there is nothing but a black hole, an object with no surface, no features, no memory of the star that came before. The existence of this line also means that neutron stars live on borrowed time. Many are in binary systems, siphoning material from a companion star. As they grow heavier, they creep closer to the threshold. Others may collide with fellow neutron stars, merging into a single object whose mass is too great to endure. In each of these cases, the fate is the same. Once the Tolman-Oppenheimer-Volkoff limit is passed, the neutron star loses its identity in an instant. Gravity wins, and the object disappears behind an event horizon. This knowledge leaves us with a haunting perspective. Neutron stars are not the end of the story of stellar death. They are the penultimate chapter, the guardians of survival, before the inevitable surrender. Their very existence proves that matter can hold out against gravity for a time, but their fate reminds us that gravity always has the final word. The story of neutron stars is therefore a story of limits. It is the story of how the universe balances on razor-thin edges, where the addition of a single solar mass can decide the difference between endurance and collapse. It is the story of how the quantum laws that protect matter eventually fail in the face of gravity's demand. And it is the story of how stars, even in death, continue to shape the cosmos by approaching the threshold of collapse. As we step from this chapter into the next, we move directly into the mystery of this threshold. What is the precise value of the Tolman-Oppenheimer-Volkoff limit? How do we measure it? And what happens in the moment when a neutron star, pushed just beyond its capacity, collapses into the blackness of a black hole? This is where we now turn into the razor-thin line between survival and annihilation. In the earliest days of general relativity, when Einstein's equations were still fresh and the cosmos was being reimagined, physicists asked a daring question. If gravity could bend space and slow time, if it could hold entire galaxies together, what would happen when matter was pushed to its absolute limit? For ordinary stars, the answer was already clear. Their collapse could be halted by nuclear fusion or, in the case of white dwarfs, by electron degeneracy pressure. But what of neutron stars? Those collapsed remnants where matter is compressed into its barest essence. Could they resist forever? Or was there a point beyond which nothing could survive? This question was answered, at least in theory, in the 1930s, when Richard Tolman, J. Robert Oppenheimer, and George Volkoff worked through the equations of relativistic hydrostatics. Their result became known as the Tolman-Oppenheimer-Volkoff limit, a theoretical maximum mass for neutron stars. It is not an arbitrary boundary. It arises directly from the marriage of general relativity and quantum mechanics, from the interplay between gravity and degeneracy pressure. It says simply this: there is a maximum mass A neutron star can carry before its neutrons themselves are crushed beyond recognition, and once that limit is passed, the star collapses into a black hole. The equations that define this limit are uncompromising. They describe a balance between the inward pull of gravity and the outward push of pressure inside the star. At lower masses, the degeneracy pressure of neutrons is sufficient, but as mass increases, gravity curves space-time more severely, making the star's own weight heavier in a relativistic sense. At some point, no equation allows a stable solution. The mathematics itself collapses, leaving no option but further gravitational collapse. This is the Tolman-Oppenheimer-Volkoff limit, the point where nature itself says no star can exist. Observationally, we know this limit must lie somewhere between 2 and 3 times. The mass of the Sunday neutron stars have been measured with masses close to 2 solar masses, and they remain stable. But we have never seen one beyond 3 solar masses. Instead, at those higher masses, we find only black holes. The silence between these two observations tells us the boundary lies there, though its precise value depends on the details of how matter behaves at extreme densities, details that remain one of the deepest mysteries in physics. It is a strange kind of boundary. Unlike the edge of a cliff or the surface of a star, the Tolman-Oppenheimer-Volkoff limit is not something you can see or touch. It exists only in equations and in the behavior of matter under crushing weight. Yet it is as real as any mountain, and far more absolute. A neutron star approaching this limit has no warning system. It does not wobble or tremble. The moment it crosses the line, collapse is instantaneous. The neutrons, unable to resist further compression, give way, and the star disappears into the darkness of a black hole. To understand the precision of this limit is to appreciate its drama. A neutron star with just under 2 solar masses can spin for billions of years, sending out steady pulses of radio waves. Add half a solar mass, and it collapses entirely. That half mass is the difference between endurance and annihilation, the difference between a star that can be studied and a black hole that hides everything behind its event horizon. Few thresholds in nature are so stark. What the Tolman-Oppenheimer-Volkoff limit truly represents is the final defeat of matter by gravity. It shows us that even the most fundamental particles we know cannot resist forever. The neutron, that sturdy building block of atomic nuclei, is no match for gravity when mass grows too large. At the threshold, neutrons dissolve, and the star is consumed. It is here that the universe draws its most uncompromising line. And yet, this line is also a source of curiosity. Could there be states of matter beyond neutrons, exotic phases like quark matter or strange matter, that allow a star to survive a little longer before collapse? Could the Tolman-Oppenheimer-Volkoff limit be shifted slightly upward by the presence of these exotic forms? Some theorists imagine the possibility of quark stars, objects more compact than neutron stars but not yet black holes. If they exist, they would blur the line between survival and collapse. But even they would not escape the eventual triumph of gravity. The Tolman-Oppenheimer-Volkoff limit is flexible only within narrow bounds. It does not vanish. It waits. As we leave this chapter, the image is clear. A neutron star is a survivor, but only up to a point. The Tolman-Oppenheimer-Volkoff limit defines the razor-thin boundary between existence and oblivion. It is the invisible cliff over which neutron stars fall when they grow too heavy. And it is the final word gravity speaks to matter. Beyond it, there is no star, no surface, no pulse of radiation. There is only a black hole. The story of the Tolman-Oppenheimer-Volkoff limit is as much about history as it is about physics. In the 1930s, when Einstein's theory of general relativity was still young, the cosmos was being reimagined. Astronomers had only recently discovered that the universe was expanding, and the very idea of stellar collapse was still radical. White dwarfs had been identified as faint remnants of stars, and the work of Subrahmanyan Chandrasekhar had shown that they too had a maximum mass, about 1.4 times the mass of the Sun, beyond which electron degeneracy pressure could not hold. That limit became known as the Chandrasekhar limit, and it laid the groundwork for a deeper question. If electrons could fail, what about neutrons? Richard Tolman, working at Caltech, studied the structure of stars within the framework of general relativity. His student, George Volkoff, joined forces with J. Robert Oppenheimer, who was not yet the figure known for the atomic bomb, but already a mind probing the mysteries of the universe. Together they applied relativity to the problem of neutron stars, which had just been proposed by Lev Landau and Walter Bade. They asked the simplest and most terrifying question: how heavy can such an object be before it collapses into something even stranger? The equations they derived were exacting. They combined relativity, which describes how gravity warps space-time, with the pressure equations for degenerate neutrons. The result revealed that there is no infinite resistance. Just as the Chandrasekhar limit defines the maximum mass for white dwarfs, the Tolman-Oppenheimer-Volkoff limit defines the maximum mass for neutron stars. Above it, no static solution exists. The equations have no stable star, only collapse. Their work, published in 1939, was largely overshadowed by the looming World War, but it remains one of the foundational results in astrophysics. Decades later, the discovery of pulsars in 1967 provided the first observational evidence that neutron stars were real. Jocelyn Bell Burnell and Anthony Hewish detected the regular radio pulses of a spinning neutron star, and suddenly, the Tolman-Oppenheimer-Volkoff equations were not just theory, they described real objects scattered across the galaxy. Over time, astronomers found heavier and heavier neutron stars, each one a test of the theoretical limit. Yet the precise value of the Tolman-Oppenheimer-Volkoff limit is still uncertain. It depends on the equation of state of nuclear matter, the relationship between pressure and density, under conditions far beyond laboratory reach. Do neutrons remain intact deep inside the star, or do they break down into quarks? Does exotic matter like hyperons or kaons appear? Each possibility shifts the limit slightly. A stiffer equation of state allows heavier neutron stars, pushing the limit toward 3 solar masses. A softer equation of state lowers the limit, closer to 2. We do not yet know which is correct. Observations help to narrow the range. In 2010, astronomers measured a neutron star nearly 2 times the mass of the Sun, straining the lower edge of the limit. More recent discoveries have confirmed neutron stars in the range of 2.1 to 2.2 solar masses. These observations rule out many softer equations of state. At the same time, no neutron star heavier than about 2.5 solar masses has ever been observed. Above that, the universe offers only black holes. This silence is as telling as any detection. It tells us that the Tolman-Oppenheimer-Volkoff limit is real, and that nature enforces it without compromise. What makes this limit so haunting is how narrow it island. Between 2 and 3 solar masses lies the razor-thin window in which neutron stars can exist. Below it, the degeneracy pressure of neutrons holds the line. Above it, collapse is inevitable. There is no slow transition, no gradual blurring. The star crosses the line and vanishes behind an event horizon. The fact that such a small addition of mass can determine the fate of an entire star is one of the starkest examples of gravity's authority. The Tolman-Oppenheimer-Volkoff limit is therefore not just a number in physics. It is a threshold in reality. It is the moment when matter itself fails, when even the most fundamental particles we know cannot resist the pull of space-time. It is the gateway to black holes, and it tells us that survival in the cosmos is always conditional. For neutron stars, that condition is written in their mass, and it is enforced by gravity, with no exceptions. As we approach the conclusion of this chapter, we must recognize what this limit represents. It is not merely the end of neutron stars. It is the demonstration that gravity is not simply one force among others. It is the ultimate judge of cosmic fate. And it reminds us that even in the universe's most extreme survivors, balance is temporary. Collapse always waits. The Tolman-Oppenheimer-Volkoff limit is not just a number etched into equations. It is a border written into the very fabric of space-time. When a neutron star approaches it, the balance that has held since the supernova begins to teeter. The neutrons, already crushed against one another, can resist no further. Their quantum pressure, that invisible barrier, falters under the weight of the star itself. At that moment, the star ceases to be what it was. There is no gradual transition, no long decline. It is an instantaneous surrender. To imagine this collapse is to step into one of the universe's most dramatic transformations. Picture a neutron star quietly spinning, perhaps pulsing radio waves like a lighthouse in the void. For millions of years it has survived. Then, as matter accretes from a companion star, or as two neutron stars merge, its mass creeps upward. The moment the Tolman-Oppenheimer-Volkoff limit is crossed, gravity floods in unchecked. The surface, the crust, the neutrons themselves, all fall inward. The star does not explode outward this time. It implodes, shrinking beyond its own identity, until only an event horizon remains. The collapse is final. From the outside, the neutron star vanishes. Light that once escaped as pulses is cut off. Magnetic fields that once arched into space are swallowed. The entire history of the star is erased, replaced by a black hole characterized only by mass, spin, and charge. Everything else is lost behind the veil. The Tolman-Oppenheimer-Volkoff limit is therefore not simply a theoretical curiosity. It is the switch that turns a neutron star into a black hole. It is the line between survival and disappearance. This limit also tells us something profound about the universe. It tells us that matter itself is not absolute. The neutron, one of the most stable particles we know, cannot endure infinite compression. There is always a scale of gravity large enough to defeat it. The Tolman-Oppenheimer-Volkoff limit is the signature of this truth. It is nature's reminder that gravity is the ultimate authority. Other forces can resist for a time, but none can resist forever. And yet, in the details of this limit, lie mysteries we have not solved. Is the threshold closer to 2 solar masses, or does exotic matter allow stars as heavy as 3 solar masses to survive? Could quark matter provide a temporary reprieve before collapse? Observations push us closer, but we do not yet have the final answer. In every neutron star we weigh, in every merger we observe, we inch nearer to understanding. For now, we stand at the edge of knowledge. We know that neutron stars cannot survive beyond a certain mass, but we do not know the exact value of that mass. We know collapse follows instantly, but we cannot yet see inside the moment of surrender. The Tolman-Oppenheimer-Volkoff limit is both a discovery and an invitation. It tells us where the line lies, but it also dares us to learn how nature enforces it. As this chapter closes, the narrative sharpens. Neutron stars are survivors, but not beyond their limit. They are guardians of a fragile balance, but that balance ends the moment their mass tips too far. What follows is not survival, but collapse. And collapse, once it begins, is absolute. In the next chapter, we will follow that collapse step by step. We will see how a neutron star crosses the threshold, how it implodes under its own weight, and how the universe transforms an object of matter into an object of pure space-time. This is the moment when gravity wins. The Tolman-Oppenheimer-Volkoff limit stands as an invisible frontier, a law etched into space-time itself. But laws in physics are not abstract. They manifest in real events. Neutron stars do not sit frozen forever at the edge of stability. They live in a universe filled with companions, collisions, and chance encounters. And in that restless cosmos, there are many ways for a neutron star to be pushed beyond its fragile balance. Collapse is not a myth. It happens, and when it does, the transformation is among the most violent spectacles the universe can stage. For millions or billions of years, a neutron star may survive quietly, Alone, it spins, radiating faintly, cooling slowly. But in binary systems, survival is less certain. When paired with a massive companion, the neutron star may feed, pulling in gas and plasma from its partner. This accretion, steady or explosive, adds mass grain by grain. Each addition deepens gravity's hold, each addition tightening the noose around degeneracy pressure. At first, the star endures, flaring with X-rays as matter slams into its surface. But the accumulation cannot continue forever. One day, imperceptibly, the critical mass is crossed. In that instant, the balance snaps. Sometimes the path to collapse is more sudden. Neutron stars exist not only in binaries with ordinary stars, but also with other neutron stars. When they orbit closely, their dance is a death spiral. Gravitational waves radiate away energy, shrinking the orbit until the two collide. The merger is catastrophic. Shock waves rip through the stars, matter ejects at nearly light speed, and heavy elements are forged in the firestorm. If the combined mass is too great, the remnant cannot survive even for a second as a stable neutron star. It collapses instantly, vanishing into a black hole. In this way, neutron star mergers become engines of cosmic alchemy, seeding galaxies with gold and platinum, while also feeding the population of black holes. Even the supernova itself can birth a star too heavy to endure. When a massive star dies, the collapsing core may already exceed the Tolman-Oppenheimer-Volkoff limit. In that case, no neutron star is born at all. The core implodes directly into a black hole. From the outside, the difference is subtle. The explosion still rips apart the star. The light still outshines an entire galaxy. But at the center, the story is written in gravity alone. If the mass is too great, collapse happens immediately, and the black hole begins its existence in the first heartbeat after the supernova. In all these scenarios, the principle is the same. Gravity waits for opportunities, and the universe provides them. Whether through accretion, mergers, or overmassive births, neutron stars are often doomed to exceed their limit. When they do, the transition is swift. The star has no defense left. The neutrons collapse into one another, their identities dissolved, and space-time itself folds inward. To watch such a collapse, if one could survive long enough to see it, would be to witness silence overtaking violence. The neutron star, once a source of pulses and fields and light, is snuffed out. What remains is darkness, not because it emits nothing, but because nothing, not even light, can escape. It is an ending, but also a beginning. For the black hole that forms will live longer than the stars, longer than galaxies, perhaps longer than the universe itself, and so the path is clear. Neutron stars are not immune, their balance is fragile, and the cosmos is full of events that tip them over the edge. Collapse is not an accident, but an inevitability. It is how the universe turns matter into mystery, how it replaces something we can study with something we cannot. When gravity wins, the neutron star disappears, and in its place arises an object beyond comprehension. In the next chapter, we will follow that transformation more closely, tracing the moment when a surface vanishes, when light fails to escape, and when density ceases to be a number at all. We will witness the neutron star's final fall into the abyss of a black hole. When a neutron star begins to accumulate mass from its environment, the process is not quiet. If it has a companion star, gas and plasma flow from the larger star toward the compact remnant, spiraling inward in a luminous accretion disk. Friction in that disk heats matter to millions of degrees, radiating in powerful bursts of X-rays. Each grain of mass that falls inward deepens the star's gravity well, pressing the neutrons tighter. For a long while, the balance holds. The star survives, glowing with energy stolen from its partner, but accretion is steady and merciless. One solar mass gained in this way can decide the difference between existence and collapse. The instant the Tolman-Oppenheimer-Volkoff limit is surpassed, the neutron star does not pause. It gives way, and the collapse begins. In neutron star mergers, the pathway is far more violent. Two stars locked in orbit lose energy through gravitational radiation, spiraling closer over millions of years. When they collide, the violence is beyond imagination. Shock waves race outward, nuclear matter is ripped apart, and entire mountains worth of gold and platinum are hurled into space. The remnant left behind is usually unstable. If the combined mass is greater than the critical threshold, the merged object collapses in moments. What began as two stars ends as one black hole, its formation punctuated by bursts of gamma rays and waves in space-time itself. These mergers are not just cosmic catastrophes, they are also the crucibles in which the heaviest elements of the universe are forged, the very metals in our bones and blood born in the deaths of stars. Even in solitary death, a neutron star may never truly exist. Some massive stars collapse so violently that their cores already exceed the Tolman-Oppenheimer-Volkoff limit. In these cases, there is no neutron star stage at all. The collapse proceeds uninterrupted. The star's core implodes directly into a black hole, while the outer layers explode outward in a supernova. To an observer, the explosion might look the same as one that leaves behind a neutron star. Yet deep within, the fate is different. Instead of a survivor, the star gives birth to an abyss. Across all these pathways, the principle is identical. Collapse happens when gravity's weight grows stronger than the defenses of degeneracy pressure. Whether the mass is added slowly from a companion, delivered suddenly in a merger, or born too heavy from the start, the result is the same. When the critical mass is reached, the star crosses a one-way boundary. The neutrons no longer hold their line. Space-time folds inward, the surface disappears, and the identity of the star is erased. To witness such a collapse would be to see finality itself. The pulses of radiation stop. The surface vanishes. The neutron-packed heart that once balanced against gravity is consumed in silence. What remains is a black hole, invisible, yet more enduring than the star that gave birth to it. This is how collapse happens, not as a possibility, but as a certainty written into the laws of the cosmos. In the next part, we will follow the mechanics of this transformation more closely, tracing how the implosion builds, how the event horizon forms, and how a neutron star becomes something beyond matter entirely. When the final moment comes, the collapse of a neutron star is not a gradual fading, but a sudden implosion. Inside, the neutrons are pressed together beyond the threshold allowed by physics. Degeneracy pressure, which once held the star up against gravity, yields at last. The core gives way, and the star begins to fall inward. Unlike a supernova, which hurls matter outward in a blast of light and energy, this is an implosion directed entirely toward the center. Every layer of the star, every particle within it, accelerates downward, pulled into a shrinking sphere that no longer has the strength to resist. The speed of this collapse is staggering. The star contracts in milliseconds, a heartbeat on a cosmic scale. Space-time around it curves more and more violently. Photons that once streamed into the universe bend back toward the collapsing star. Unable to escape, the magnetic fields, so immense in life, are dragged inward and twisted. If the star was once a pulsar, sending out rhythmic beacons across the cosmos, those pulses end without ceremony. Silence replaces signal. Darkness replaces light. As the collapse tightens, the star approaches the formation of an event horizon. This is the boundary where escape becomes impossible. The point where even light, traveling at the fastest speed in nature, cannot outrun gravity. The horizon forms not as a visible shell, but as an invisible frontier. To an outside observer, matter seems to slow as it approaches. Light redshifts to invisibility, and the star appears to freeze in time. But from the star's perspective, the collapse continues unstoppably inward. The event horizon seals the transformation, Outside, the neutron star vanishes. Inside, gravity rules without resistance. At this point, the concept of density ceases to have meaning. We can say the star has collapsed beyond neutron matter, beyond quarks, beyond anything we understand. General relativity tells us the core falls into a singularity, a point of infinite density and zero volume. Physics itself fails here, our equations dissolving into infinities. What remains certain is that the neutron star no longer exists as a physical body. It has become a black hole, a region defined only by its mass, its spin, and its charge. The transformation is profound. A neutron star is still a thing we can study, its surface measurable, its pulses detectable. A black hole is not. Its surface is gone, replaced by an event horizon that hides everything beyond. The collapse erases identity. The neutron star's crust, its magnetic fields, its very particles, all are swallowed, leaving only a blank presence in the fabric of space-time. This is how collapse happens. It is swift, absolute, and final. A neutron star, a survivor on the razor's edge of physics, reaches its limit and vanishes. What follows is not destruction in the ordinary sense. It is transformation. The matter that once fought against gravity now fuels its victory. The result is a black hole, an object that embodies gravity itself. With this, the path is complete. Neutron stars, born from violence, survive only for as long as their mass allows. Once they cross the Tolman-Oppenheimer-Volkoff limit, they collapse without hesitation. In the next chapter, we will follow that transformation in detail, exploring how a neutron star becomes a black hole, how horizons form, and how the universe replaces matter with mystery. The instant a neutron star crosses the Tolman-Oppenheimer-Volkoff limit, its identity begins to unravel. The pressure of neutrons, that last bastion of quantum resistance, gives way under the weight of gravity. What follows is a transformation not into fire or fragments, but into silence. The neutron star, once balanced on the razor's edge of survival, collapses inward, and in doing so, it ceases to be a star at all. The collapse is fast. A city-sized object shrinks in milliseconds, its surface racing inward until it disappears entirely. For an outside observer, light emitted from the surface redshifts, its wavelength stretched longer and longer as the star's gravity deepens. The pulses of radiation that once announced the star's presence flicker and fade. At the critical moment, the escape velocity at the shrinking surface reaches the speed of light. An event horizon forms, the point of no return, and the star vanishes behind it. The neutron star is gone. A black hole remains. The event horizon is not a surface in the ordinary sense. There is nothing to touch, no material shell. It is a boundary in space-time itself, the invisible frontier where trajectories bend inward and never outward. Cross it, and escape is impossible, no matter how fast you move, no matter what energy you carry. The black hole is born not as a new kind of matter, but as a new geometry. It is space-time folded inward on itself, shaped by gravity, so intense that even light cannot trace a path out. The difference between crushing density and infinite collapse is profound. A neutron star is still an object of matter, with a surface and structure we can describe. Its density is beyond imagination, but it is finite. In a black hole, the collapse does not stop. General relativity tells us the star's matter continues inward until it compresses into a singularity, a point of zero volume and infinite density. At this point, the laws of physics as we know them break down. Equations give infinities, and our descriptions fail. The singularity is not just a region we cannot see. It is a region we cannot yet understand. Yet from the outside, none of this complexity is visible. The black hole is a simple object, defined only by mass, spin, and electric charge. All other details of the neutron star, the composition of its crust, the shape of its magnetic fields, the arrangement of its neutrons are lost. Physicist John Wheeler described this as, "Black holes have no hair. They are stripped of identity. All that remains is their gravitational influence, a presence that bends light, warps time, and alters the paths of stars and gas around them." This transformation, from neutron star to black hole, is not destruction in the traditional sense. Nothing is obliterated into nothingness. Rather, everything is consumed into space-time itself. The matter that once defied gravity now fuels it. The result is an object, not of substance, but of geometry. A black hole is not matter, but a place where the rules of matter have given way entirely to the rules of gravity. The transition is absolute. The neutron star does not linger, does not partially survive. Once collapse begins, the event horizon forms, and all trace of the star is hidden. What was once a spinning beacon, a pulsar, or a magnetar, becomes a silence in the sky. Its presence is known only through what it does to its surroundings, the way it bends starlight, the way it tears apart companions, the way it warps space-time with its motion. This is the fate of the heaviest neutron stars. They are survivors, but only up to the limit. Beyond it, they surrender completely. In this surrender, they give birth to the universe's most enigmatic objects. Black holes are not just the death of stars. They are the beginnings of mysteries that still elude physics. They mark the places where our theories fail, where gravity outpaces our understanding, and where the universe hides its most guarded secrets. As this chapter closes, we see the transformation complete. A neutron star, once matter's last stand, collapses into a black hole, an object without surface, without escape, without identity. In the next chapter, we will look outward again, at how we observe this transformation across the cosmos. Through gravitational waves, gamma-ray bursts, and the remnants of supernovae, we are beginning to witness collapse itself. The silence of a neutron star becoming a black hole is not truly silent. It leaves behind echoes that carry across the universe. As the neutron star crosses its fatal boundary, the view from outside grows stranger still. To a distant observer, the star does not collapse all at once. Instead, light emitted from its shrinking surface struggles to climb out of the deepening gravitational well. Each photon loses energy on its way upward, its wavelength stretched longer and longer. What began as X-rays and gamma rays fades into visible light, then into infrared, and finally into radio waves, too faint to detect. From our perspective, the neutron star appears to slow, its collapse stretched across time, its pulses dwindling into silence. In truth, the collapse continues inexorably. It is only relativity's trick, the warping of time near extreme gravity, that creates the illusion of slowing. At the moment the event horizon forms, the universe redraws its rules. This horizon is not a material wall. It is a geometric threshold, defined by the point at which the escape velocity equals the speed of light. Nothing that passes this boundary can ever return. The horizon swallows not only matter, but also information. The detailed history of the neutron star, the precise arrangement of its magnetic field, the chemistry of its crust, the subtleties of its internal structure are erased from view. From beyond the horizon, all observers see the same blank object. The individuality of the neutron star vanishes in a single act of collapse. Time itself behaves differently near the newborn black hole. For a falling particle, the journey inward lasts only seconds. For an outside observer, the approach to the horizon is stretched into eternity. This paradox is not a flaw, but a feature of relativity. It tells us that collapse is both sudden and eternal, both a vanishing in moments and a freezing in time. The event horizon is the ultimate boundary, where perception fractures and the universe divides what can be seen from what can never be known. The magnetic fields of the neutron star, so immense and complex, are dragged into the collapse as well. Some may reconnect and flare before the horizon forms, releasing energy in bursts of radiation. Others may be twisted and swallowed whole, locked forever inside. If the star was once a pulsar, its precise rhythm ends abruptly. The lighthouse beam that swept across space ceases, replaced by silence. For astronomers, such an end would look like a star that simply stopped speaking, cut off mid-sentence, leaving only emptiness, where once there was a pulse. This disappearance is not destruction in the fiery sense of an explosion. It is annihilation through concealment. The matter of the neutron star is still there, but it has been pulled into a region where the laws of physics hide it from the universe. What was once an object with a surface, with properties we could measure, has become a place defined only by absence. The black hole reveals nothing of the star that created it. Whether it was born from accretion, a merger, or an overmassive core, the result is indistinguishable. Only mass, spin, and charge remain, the rest erased. For those who study the cosmos, this transformation is both frustrating and profound. It is frustrating because it hides answers. We desperately seek answers about matter at nuclear densities, about the behavior of quarks and gluons under crushing pressure. But it is profound because it reveals something deeper, that gravity is not merely a force, but a sculptor of reality itself. It shapes space-time into horizons and singularities, and in doing so, it limits what can be known. This is the essence of the collapse from neutron star to black hole. It is not an explosion, but a vanishing. It is not chaos, but silence. It is the erasure of individuality, the stripping away of detail, the reduction of a complex star into a simple geometry. And yet, in that simplicity lies power. Black holes endure longer than any star, their horizons persistent, even as galaxies change and fade. In consuming a neutron star, gravity creates something more permanent, more mysterious, and more essential to the cosmic story. From here, the narrative leads us deeper still. In the next part, we will follow the collapse beyond the horizon, into the realm where relativity predicts singularities, and where density and time lose their meaning. This is the true heart of transformation, where matter becomes mystery, and where the universe itself reaches the edge of comprehension. As the collapse continues past the event horizon, the neutron star ceases to exist in any recognizable sense. From outside, all that can be seen is the black hole that now replaces it, a region of space-time, stripped of features, defined only by mass, spin, and charge. Inside the horizon, however, the story deepens into realms that physics cannot yet fully describe. The matter of the star, the neutrons and quarks and particles that once defied gravity, are carried inward on a path that ends at the singularity. General relativity predicts that this singularity is a point of infinite density, where volume vanishes and curvature of space-time diverges without limit. The equations offer no comfort here. They yield infinities, numbers that have no physical meaning. What this really means is that our understanding fails. Relativity, powerful as it is, does not provide answers inside a black hole. Quantum mechanics, the other pillar of physics, offers hints, but no complete picture. Somewhere at the singularity, a deeper theory must wait, one that unites gravity with the quantum world. But until that theory is found, the singularity remains a symbol of mystery, the place where knowledge stops. From the perspective of the collapsing star, everything is drawn inward, irresistibly. Distances shrink, time itself distorts, and in less than a second by its own clock, the material of the neutron star has been consumed. The surface, the crust, the superfluid core, all are gone. In their place is the geometry of space-time, folded inward, a structure invisible to the universe beyond. What was once matter has been converted into the shape of a gravitational well, deeper and darker than anything else in nature. The difference between crushing density and infinite collapse is crucial. A neutron star, though impossibly dense, is still a material object. It has a crust, it has layers, it has a measurable radius. A black hole has none of these. It is not matter, but an event in space-time, a region where the rules of matter give way entirely. The collapse from one to the other is not a change of state, like ice melting to water. It is a change of category, the disappearance of matter into geometry, the replacement of substance with absence. Yet black holes are not completely silent. In their births, they leave signatures, bursts of gravitational waves, flashes of gamma rays, disruptions in their environments. The collapse of a neutron star into a black hole is not entirely hidden. It may shake the fabric of space-time in ways we can detect, and it may scatter the last cries of energy before the horizon forms. These signals are rare, fleeting, and faint, but they are clues that the transformation has taken place. They are the universe's whispers of a star's final surrender. Once the black hole has fully formed, it becomes one of the most enduring structures in the cosmos. Stars burn out, galaxies evolve, but black holes persist. They will outlive everything else, surviving even into the far future when the universe grows cold and dark. The neutron star, fragile and temporary, has been replaced by something eternal. This is not destruction, but permanence. Gravity's victory is not to erase, but to create an object that endures longer than any star could dream. The transformation from neutron star to black hole is therefore both an ending and a beginning. It is the ending of matter as we know it, the ending of individuality, the ending of surfaces and signals. But it is also the beginning of something more fundamental, an object that embodies space-time itself. It is the moment when gravity ceases to be resisted and becomes absolute. As we leave this chapter, the collapse is complete. The neutron star, once a monument to survival, is gone. In its place is a black hole, a mystery deeper than any star, a silence louder than any explosion. In the next chapter, we will turn our gaze outward once more, to the instruments and observations that allow us to witness these transformations across the universe. Through gravitational waves, bursts of light, and the scars left on galaxies, we are learning to see the unseen, to hear the silence, to trace the moment when gravity wins. The collapse of a neutron star into a black hole is hidden behind an event horizon, but the universe is not entirely silent. Though the star itself vanishes from view, the process leaves echoes, ripples, and scars that can be traced across space. For centuries, such events were beyond imagination. Even when the concept of black holes was proposed in theory, they were thought to be undetectable, forever cloaked in invisibility. But the universe leaves clues for those who know how to look. Today, with instruments that stretch the limits of engineering and patience, we have begun to catch these whispers of collapse. Wei Hum, Wei, 10, ICA. One of the most dramatic ways we observe these transformations is through gravitational waves. When neutron stars orbit each other and eventually collide, their dance stirs the fabric of space-time itself. Ripples spread outward at the speed of light, stretching and compressing the distance between objects by less than the width of a proton. It took a century from Einstein's prediction before humanity built machines sensitive enough to detect such waves. In 2015, the LIGO observatories in the United States first heard the faint tremor of two black holes merging. Just 2 years later, in 2017, came the moment that changed astrophysics forever: the detection of two neutron stars colliding. That event, called GW170817, sent both gravitational waves and light across the cosmos. As the waves swept past Earth, telescopes worldwide turned to the sky. They saw a fireball of radiation, a kilonova, the afterglow of colliding neutron stars, ejecting matter at relativistic speeds. Within days, astronomers detected heavy elements forming in the debris, confirming that such collisions forge gold, platinum, and other heavy metals. And while the merger began with neutron stars, the combined mass was too great for the remnant to endure. Within seconds, the object collapsed into a black hole. For the first time, we had witnessed, through both light and gravity, the birth of a black hole from neutron star collapse. But not all collapses are so grand. Some happen in quiet binaries, where a neutron star feeds on its companion star. As mass flows steadily onto the remnant, X-ray flares reveal the violence of accretion. Astronomers can watch as the neutron star grows heavier, creeping closer to its limit. One day, if enough mass accumulates, the pulses of radiation may simply stop. The star will have collapsed. Though we cannot see inside, we will know by the silence, the absence of signal, that a black hole has formed. In the language of astronomy, sometimes disappearance is itself the clearest evidence. Other times, the clues arrive in gamma-ray bursts, the most energetic explosions in the universe. Some short bursts are thought to mark the moment when neutron stars merge and collapse, releasing jets of energy that outshine entire galaxies. These bursts, lasting less than 2 seconds, are signatures of sudden death, the final cry of matter before being sealed behind a horizon. Though we cannot watch the collapse itself, these flashes are beacons that tell us where and when gravity has won. Even supernova remnants carry their secrets. In some, we find a neutron star at the center, spinning or pulsing as expected. In others, there is only a void. The absence suggests that the collapsing core of the star exceeded the Tolman-Oppenheimer-Volkoff limit from the beginning, forming a black hole instead. The shell of gas and dust expands outward, a brilliant monument to destruction, but at the center, no pulsar shines. The silence marks the collapse. Observing these transformations is still in its infancy. Our instruments are only beginning to detect the signals with precision, and our theories are still catching up with the data. Yet each detection is a confirmation of the grand narrative. Neutron stars are not immortal. They can and do collapse. And though the collapse itself hides behind a horizon, the universe is generous in leaving clues at the edges. In the next part, we will follow these observations more closely, from the delicate tremors of gravitational waves to the blinding brilliance of kilonovae, and see how they are rewriting our understanding of collapse and survival in the cosmos. When the LIGO detectors in Louisiana and Washington first felt the tremor of space-time in 2015, the world of astronomy changed. Humanity had built machines capable of measuring distortions smaller than the width of a proton, instruments so sensitive they could detect the collision of black holes 1 billion light-years away. These were not telescopes in the traditional sense. They did not gather light, but instead listened to the vibrations of reality itself. With LIGO, and later Virgo in Italy, we gained the ability to hear the universe in a new way. The event of August 17, 2017 was the watershed. 2 neutron stars, each heavier than the Sun, but only 20 kilometers across, spiraled into each other. As they merged, their gravitational waves passed through Earth, ringing the detectors in a pattern unmistakable to physics. What followed was a global race. Observatories across the world turned to the patch of sky where the signal had originated. They saw the fading light of a kilonova, an explosion unlike any ordinary supernova. The spectra revealed the fingerprints of newly forged elements, gold and platinum among them, created in the furnace of collision. It was not just a cosmic collision. It was the birth of heavy matter and the death of neutron stars. Within seconds, the remnant collapsed into a black hole, hidden from sight, but revealed by its aftermath. This single detection confirmed theories long suspected. It proved that neutron star mergers were factories for the heaviest elements, and that they could collapse into black holes. It showed that gravitational waves and light could be observed together, inaugurating an era of multi-messenger astronomy. Most importantly, it gave us the first observational glimpse of a neutron star's collapse. Not in direct sight, but in echoes, waves in space-time, and bursts of radiation across the spectrum. But collapses do not always announce themselves so loudly. Some happen in silence, detectable only through absence. Astronomers who study pulsars know their rhythms intimately, measured to microseconds. When a pulsar's radio beams cease without explanation, one possibility is collapse. If the neutron star accreted too much mass, if it crossed the invisible threshold, it may have surrendered to gravity. The star is no longer visible, but its silence is as telling as its presence once was. Disappearance is data. Then there are the gamma-ray bursts, flashes of high-energy light lasting mere seconds but shining brighter than galaxies. Many short gamma-ray bursts are thought to arise from neutron star mergers that collapse swiftly into black holes. The burst is the final jet of energy, beamed into space before the horizon closes. For astronomers, these bursts are signposts. They tell of collapse happening at cosmological distances, collapses that we cannot see directly, but can infer from the violence of their signals. Even supernova remnants whisper of collapse. The Crab Nebula holds a pulsar at its heart, proof that its progenitor star collapsed into a neutron star. But other remnants contain nothing. Their centers are voids, not because the collapse left no trace, but because it left a black hole. The absence of a pulsar where one should exist suggests that the collapsing core exceeded the Tolman-Oppenheimer-Volkoff limit from the start. These silent centers are monuments to collapse, black holes wrapped in shrouds of gas and dust. The more we watch the sky, the more we see that collapse is not rare. It happens often, in binaries, in mergers, in massive stellar deaths. And each time, though the star itself vanishes, the universe leaves marks, ripples, flashes, absences that reveal the transformation. Collapses are hidden, but not entirely. With the right tools, we can trace their outlines. In the next part, we will explore how these observations accumulate into a larger picture, how every detection teaches us more about the boundary between survival and collapse, and how the universe itself has become our laboratory for watching gravity win. Each observation of collapse adds a brushstroke to a vast cosmic painting. Gravitational waves give us the rhythm, gamma-ray bursts give us the flash, and supernova remnants give us the silence. Together, they create a narrative that is now undeniable. Neutron stars do not endure forever. They may survive for millions or even billions of years, but in the end, gravity reclaims them. What was once hidden behind theory has now been witnessed in practice, not once, but many times, scattered across the universe. The gravitational waves recorded by LIGO and Virgo are not vague signals. They are fingerprints. The chirp of two neutron stars spiraling together carries information about their masses, their spins, and their final fate. When the waves cut off abruptly, it is not because the stars disappeared into nothing, but because they collapsed into a black hole. The signal is silence, but a silence with meaning. Each detection narrows the range of the Tolman-Oppenheimer-Volkoff limit. Each one tells us more about how close neutron stars can come to survival before succumbing. Gamma-ray bursts add the spectacle. These fleeting explosions, lasting only seconds, shine so brightly that they can be seen across billions of light years. Their brevity and intensity suggest catastrophic events, neutron stars merging, collapsing, and releasing jets of radiation as space-time folds inward. For astronomers, catching these bursts is like hearing a scream across the cosmos, a scream that ends abruptly as the horizon forms. The energy released is staggering, equivalent to converting entire suns directly into radiation in the blink of an eye. And then, just as suddenly, the black hole remains, silent and invisible. Supernova remnants, by contrast, are patient. Their shells of gas expand over centuries, glowing with energy from shock waves and radioactive decay. When we look into their centers, we sometimes see a pulsar, a survivor, spinning with defiance. But other times, there is nothing. The void at the heart of a supernova remnant is a clue more powerful than any flash of light. It tells us that the core collapsed too far, that no neutron star was stable enough to remain. Instead, the remnant conceals a black hole, its presence betrayed only by the absence of any beacon. These three kinds of evidence, waves, bursts, and voids, are the language by which the universe tells us of collapse. Each one is indirect, for no observation can penetrate the event horizon itself. But together, they create a mosaic. We no longer have to ask whether neutron stars collapse into black holes. We know they do, and we are learning to recognize their signatures across the sky. The power of these observations lies not only in confirming theory, but in opening new mysteries. The gravitational waves of mergers may tell us about the behavior of matter at nuclear densities. The kilonovae following collisions reveal how the elements of planets and life are forged. The silent voids in supernova remnants show us where the line between survival and collapse has been crossed. Every piece of evidence deepens our understanding of gravity's authority. We stand now at the beginning of an era. With more sensitive detectors on the horizon, we will catch these events more often, in greater detail. We will hear the universe speak of collapse, not once in a decade, but many times a year. Each signal will be another window into the frontier between matter and space-time. As this chapter closes, the transformation no longer feels hidden. We cannot see inside the horizon, but we can see enough. Across the cosmos, neutron stars are collapsing even now, some in violent mergers, others in silent surrenders. And through gravitational waves, gamma rays, and the absence of pulsars, we are already witnessing their final moments. In the next chapter, we turn to a deeper possibility. Before collapse into black holes, could neutron stars pass through stranger states of matter? Could they, for a moment, become quark stars or other exotic remnants, brief experiments by nature before gravity completes its work? For all the certainty that neutron stars eventually collapse into black holes, there lingers a possibility that nature may pause along the way. Before gravity finishes its conquest, before the horizon seals the fate of matter, could there be another form of star, stranger than anything we have yet confirmed? Some physicists believe the answer is yes. Between neutron stars and black holes may lie a hidden stage, a fleeting experiment of the cosmos quark stars. To understand this idea, we must look deeper into matter itself. Neutrons are not indivisible. Inside each neutron are quarks, bound together by gluons, particles that carry the strong nuclear force. Under ordinary conditions, these quarks are confined, never escaping the boundaries of protons and neutrons. But at extreme densities and temperatures, those boundaries may dissolve. In high-energy particle collisions on Earth, in machines like the Large Hadron Collider, we have created glimpses of quark-gluon plasma, a state where quarks and gluons move freely in a hot soup, unbound by nucleons. These collisions are brief and microscopic, lasting only tiny fractions of a second. But in a neutron star pushed to the edge of collapse, the same state might arise on astronomical scales. If the density grows great enough, neutrons could break down into their constituent quarks. The result would no longer be a neutron star, but something more compact, a quark star. Such an object would be smaller than a neutron star, perhaps only 10 kilometers across or less, but holding the same or greater mass. Its surface would not be made of neutrons, but of a sea of free quarks, up and down quarks, for certain, perhaps even strange quarks. This possibility has given rise to the idea of strange stars, where matter itself is composed of exotic particles never found in ordinary atoms. The existence of quark stars remains unproven. No observation has confirmed one, yet hints tempt astronomers and physicists alike. Some neutron stars appear unusually small for their mass, suggesting a structure denser than neutrons alone could explain. Others produce bursts of radiation that do not fit neatly into the models of pulsars or magnetars. Could these anomalies be the whispers of quark stars, objects halfway between neutron stars and black holes? The evidence is inconclusive, but the questions remain. What makes quark stars so fascinating is that they would represent matter stripped to its absolute essence. Atoms are gone, nuclei are gone, even neutrons themselves are gone. What remains is the raw fabric of matter, the quarks that build everything else. If such stars exist, they are not merely astronomical curiosities, but laboratories beyond compare. They would allow us to study the strong force, one of the most fundamental interactions in nature, under conditions utterly unreachable on Earth. But even quark stars, if they exist, cannot survive forever. They too would have a maximum mass, a limit where even the pressure of quarks cannot resist collapse. That limit would be slightly higher than the Tolman-Oppenheimer-Volkoff limit for neutrons, but not by much. Add too much mass, and the same fate awaits. The event horizon forms, and the object vanishes into a black hole. Quark stars would be way stations, not destinations, pauses in the collapse before the inevitable victory of gravity. The speculation about quark stars reminds us of something important. The line between neutron stars and black holes may not be as sharp as it seems. Nature may experiment with exotic forms of matter, creating objects that exist only briefly, hidden in rare conditions, before gravity erases them. These possibilities deepen the mystery. They show us that collapse is not simply a clean transition from star to black hole. It may pass through stages we cannot yet see, phases of matter that exist only in the hearts of dying giants. In the next part, we will dive deeper into what these exotic states might be, how quark-gluon plasma behaves, and why physicists continue to search for evidence of quark stars among the strange signals of the cosmos. Quarks are the most fundamental building blocks of matter that we know, and the idea of quark stars arises from the possibility that under immense pressure, neutrons themselves cannot remain intact. In a neutron star, the forces confining quarks inside neutrons are already strained nearly to breaking. If the density becomes too great, the neutrons may dissolve into a fluid of quarks and gluons, a state of matter that briefly existed in the early universe just after the Big Bang. In laboratories on Earth, physicists have tried to recreate this quark-gluon plasma by colliding heavy ions at near light speed. For an instant smaller than a trillionth of a second, detectors register conditions hotter and denser than the core of any star. In that instant, quarks roam free, no longer bound into neutrons or protons. It is an extraordinary glimpse into what matter may become under crushing pressure. But these experiments are tiny compared to what the cosmos can do. In the heart of a collapsing star, this state might not last a fraction of a second. It might form an entire star. Such an object, if it exists, would look outwardly similar to a neutron star, compact and dim, but its properties could reveal its difference. A quark star might be smaller for a given mass, its surface gravity even fiercer, its spin perhaps affected by the change in internal structure. Some candidates have been proposed. A few stars observed by X-ray telescopes seem too small and dense to be explained by neutron matter alone. Others show cooling rates or bursts of radiation that do not match expectations. None of these clues are decisive, but they keep the possibility alive. The idea of strange matter goes even further. If quarks combine not only as up and down varieties, but also as strange quarks, they may form an even more stable configuration. Some theorists argue that strange matter, once formed, might be the most stable state of matter in the universe, more stable even than the atoms in our bodies. If true, then a quark star could actually be a strange star, an object made of matter fundamentally different from anything we have ever touched. In such a star, the surface would not be atoms or neutrons, but a bare layer of quark soup, perhaps with a thin crust of ordinary matter floating above it. Observationally, searching for quark stars is like chasing shadows. They would masquerade as neutron stars in many ways, but with subtle differences, cooling faster, glowing differently in X-rays, or spinning with unusual regularity. Some astronomers point to anomalous pulsars and magnetars as possible candidates. Others remain cautious, arguing that all current data can be explained by extreme but still ordinary neutron stars. The debate continues, and with each new telescope, we come closer to distinguishing the two. What makes this search more than curiosity is that it touches the deepest questions of physics. The behavior of matter at nuclear densities, the limits of the strong force, the possibility of exotic stability. These are questions that cannot be answered in laboratories. Only stars can tell us. If quark stars exist, they are nature's way of revealing what matter becomes when pressed beyond all ordinary limits. Yet no matter how exotic, quark stars would still be temporary. They may resist collapse a little longer, perhaps with a higher maximum mass than neutron stars, but even they cannot resist forever. Gravity will eventually press them past their own limit, and then they too will collapse into black holes. If they exist, quark stars are waypoints, brief stops on the road from star to singularity. In the next part, we will explore this idea further, imagining what it would mean if strange matter were truly stable, how entire stars, or even the universe itself, might be affected by its discovery. If strange matter is indeed the most stable form of matter, then its existence would have consequences that reach far beyond a single star. Imagine a quark star whose surface is composed not of neutrons, nor of atoms, but of strange quark matter, a fluid sea of up, down, and strange quarks bound together. If a fragment of such matter were somehow ejected, drifting through space, theory suggests it could act as a seed, converting ordinary nuclei. It touches into strange matter as well. In this scenario, a strange star could, in principle, contaminate its environment, transforming patches of normal matter into its exotic form. Though speculative, the idea has stirred both fascination and unease. Could the universe already be dotted with hidden strange stars, their surfaces made of matter more stable than the protons and neutrons that make up us? If so, they would be difficult to distinguish from neutron stars. Their radii would be smaller, their cooling faster, their bursts perhaps more intense. But from a distance of thousands of light years, those differences blur. We may have already observed them without realizing it. Some of the most puzzling pulsars, whose signals do not fit conventional models, might be candidates. Other compact stars that seem too dense for neutron matter could also be signs. For now, the evidence is thin, the frontier uncertain, but the mere possibility expands our view of what stars can be. Whether they exist or not, quark stars and strange stars highlight the fragility of our understanding. Physics, at these densities, is beyond experiment on Earth. We rely on colliders to glimpse quark-gluon plasma, but what they create is fleeting and small. Only in the universe can such states endure, and only through careful observation can we test if they are real. This is why the search matters. A confirmed quark star would not only reshape astrophysics, it would rewrite our understanding of matter itself. Yet gravity waits even here. Quark stars may resist longer than neutron stars, but they are not eternal. Once they cross their own limit, their exotic matter is swept away, sealed inside an event horizon. The uniqueness of their state is lost to the universe, leaving only the simplicity of a black hole behind. In this way, gravity reveals its dominance again. No matter how exotic matter becomes, no matter how strange its forms, all roads end at the same destination. The possibility of quark stars is less a challenge to this truth than a deepening of it. Gravity does not destroy instantly. It allows matter to explore every configuration, to test every limit, to reveal every secret of the quantum world. It is patient. It lets neutron stars form, perhaps even quark stars, before finally claiming them. In this sense, collapse is not only an ending, but also a revelation. The universe experiments with every possibility before surrendering to gravity's final word. As this chapter closes, we stand at the edge of speculation. Quark stars and strange stars may exist, or they may not. But the possibility shows us how collapse is more than a binary between neutron star and black hole. It is a spectrum of survival, with exotic matter as brief way stations along the way. In the next chapter, we step into the aftermath of collapse itself, into the realm of black holes and the mysteries they keep hidden. When a neutron star collapses past the Tolman-Oppenheimer-Volkoff limit, it crosses a threshold beyond which no observation can follow. A black hole is born, and with it, the rules of visibility and knowledge change forever. We can describe how the event horizon forms, how the star's surface vanishes, how light is trapped, but what happens within is hidden, not only from our instruments, but from the very fabric of space-time itself. The black hole becomes a vault of secrets. And in that vault, the identity of the neutron star is lost. A neutron star is something we can still touch with theory. We can calculate its radius, estimate its crust, describe its interior, even speculate about quark matter within. It has features, properties, and individuality. But a black hole has none of these. Once collapse is complete, the details vanish. It no longer matters what the neutron star was made of, whether it contained superfluid neutrons or exotic quarks. It no longer matters if it was spinning as a pulsar, beaming across the galaxy. All of it is erased. From outside the horizon, only 3 numbers remain to describe the black hole: its mass, its spin, and its electric charge. This is known as the no-hair theorem. This stripping away of detail leads directly into one of the deepest puzzles in physics, the information paradox. If the black hole keeps only 3 numbers, what happens to all the rest of the information? The patterns of the neutron star's interior, the arrangement of its matter, the history of its pulses. Are these details lost forever, or are they somehow preserved in ways we do not yet understand? Classical relativity says they are gone, hidden beyond the horizon. Quantum mechanics insists that information cannot be destroyed. The tension between these views makes the black hole a paradox written into reality. For now, we can say only what is visible. The collapse hides everything beyond the horizon. To us, the black hole is featureless, a dark sphere in space-time that bends light and time around it. The neutron star's individuality has been erased. If we were to see a black hole formed from a neutron star merger and another from the collapse of a giant star, we would not be able to tell them apart. Their histories vanish, their differences concealed. The black hole remembers nothing but its weight, its spin, and its charge. What makes this even more mysterious is that the horizon is not an object in itself. It is a boundary, defined by gravity's geometry. Step across it, and every path forward leads only deeper toward the singularity. The neutron star's matter, once packed and balanced by quantum forces, now rushes toward a place where the very idea of matter breaks down. The singularity is not simply dense, it is beyond density. It is where space-time curves without limit, and where our equations fail. The collapse of a neutron star into a black hole is therefore not just the transformation of one object into another. It is the disappearance of knowability. Before, we could speak of neutrons, crusts, fields, and signals. After, we are left with silence. We can infer, we can model, we can speculate, but we cannot see. The collapse creates mysteries, not answers. As this chapter unfolds, we will explore those mysteries more deeply. We will consider the nature of the information paradox, the strange simplicity of black holes, and the ways in which physics itself falters at the edge of the horizon. What black holes keep hidden is not only the matter of stars, but also the limits of our understanding. Once the neutron star has collapsed into a black hole, the riddle of lost identity takes center stage. In classical relativity, the black hole is perfectly austere. Its only descriptors are mass, spin, and charge. Every other detail, the magnetic knots of the star, the quantum states of its particles, the geometry of its crust, vanishes. The neutron star, with all its individuality, is gone. What remains is an object so simple, it can be written in a single line of numbers. This is the essence of the no-hair theorem. But physics does not rest easily with such simplicity. Quantum mechanics insists that information cannot simply vanish. In the equations of quantum theory, every state is traceable, every detail preserved, no matter how complicated the transformation. To suggest that collapse into a black hole erases information is to suggest that the universe itself breaks its own laws. This is the famous black hole information paradox, a puzzle that has haunted physics for decades. Stephen Hawking deepened the paradox in the 1970s with his discovery of black hole radiation. According to quantum field theory, pairs of particles flicker into existence near the event horizon. One particle falls in, The other escapes, carrying energy away. To an outside observer, the black hole appears to radiate, slowly losing mass. Over incomprehensible spans of time, even the most massive black holes could evaporate. But if this is true, then the question grows sharper. What happens to the information about the neutron star that formed the black hole? If the whole evaporates, leaving nothing, is the information lost forever? Some physicists argue that the information is encoded in subtle correlations within the Hawking radiation. Others propose that it clings to the event horizon in a holographic form, imprinted on the surface of space-time itself. Still others suggest that our theories are incomplete, that a new framework uniting quantum mechanics and gravity must resolve the puzzle. For now, there is no consensus. The black hole stands as a mirror to our ignorance, hiding not only the matter it consumes, but the laws that govern its fate. What is certain is that collapse erases individuality from our view. A neutron star that was once measurable, describable, and unique becomes indistinguishable from any other object of the same mass and spin. If two neutron stars collapse into black holes, their differences vanish. Their magnetic fields, their compositions, their histories all gone. To the universe beyond the horizon, they are identical. This stark reduction of complexity to simplicity is one of the most haunting aspects of collapse. It is as though gravity has imposed its own aesthetic on the cosmos. Where matter once resisted with variety and structure, gravity demands uniformity. Where stars once displayed individuality, black holes reduce them to featureless voids. The neutron star's story is erased, replaced by the universal silence of the horizon. In the next part, we will follow this mystery further. We will explore how physicists wrestle with the paradox of lost information, how black holes challenge our understanding of time and space, and how the collapse of neutron stars teaches us that the universe's greatest mysteries lie not in what we can see, but in what we cannot. Once the neutron star has disappeared behind its event horizon, its past is locked away forever. The collapse has stripped it of all detail. Was it once a pulsar with a precise rhythm? Was it once a magnetar with magnetic fields strong enough to tear atoms apart? Did it contain exotic phases of matter, perhaps even a quark sea? None of these questions can be answered from outside the horizon. The black hole does not reveal its origin. Two black holes of the same mass, spin, and charge are indistinguishable, no matter how different their births were. This concealment creates one of the most profound riddles in science. If the black hole eventually evaporates through Hawking radiation, leaving nothing behind, what happens to the information about the star it once was? Physics demands that information must be preserved, yet relativity says it is lost. This clash between two great pillars of science, the quantum rules of conservation and the geometric rules of space-time, remains unresolved. Black holes are not only engines of gravity, they are engines of paradox. The collapse of a neutron star into a black hole therefore teaches us two lessons. First, it shows us the limit of survival, the moment when matter fails against gravity. Second, it shows us the limit of knowledge, the place where physics itself falters. A neutron star is still a puzzle we can piece together with telescopes and theory. A black hole is a puzzle that hides its pieces from us completely. What black holes keep hidden is not only the fate of the matter that fell in, but also the future of our understanding. They remind us that the universe has boundaries not in space, but in knowledge. They stand as monuments to gravity's triumph and to the mysteries that remain unsolved. As this chapter closes, we leave behind the collapse itself and turn to its wider consequences. In the next chapter, we will see how these collapses ripple outward across the universe, how they shape galaxies, forge elements, and seed the cosmos with the very conditions that allow life to exist. Neutron star collapse is not only an ending, it is part of the great chain of cosmic creation. When a neutron star collapses into a black hole, it appears at first to be the end of a story. The pulses of radiation cease, the surface vanishes, and the star's individuality is erased behind an event horizon. To us, Watching from afar, it seems as though the universe has extinguished a light. Yet the universe is not a place of endings alone. Each collapse reverberates outward in ways that shape galaxies, enrich planets, and alter the destiny of matter itself. Gravity, in its triumph, does not merely destroy, it creates. The first and most immediate consequence is energy. The processes that lead to collapse supernova explosions, mergers of neutron stars, and gamma-ray bursts release some of the most violent outpourings of power in the cosmos. These explosions are not just spectacular, they are factories of elements. In the furnace of neutron star collisions, conditions are so extreme that atomic nuclei absorb neutrons in rapid succession, forming the heavy elements of the periodic table. Gold, platinum, uranium, thorium, these do not emerge from the ordinary lives of stars. They are born in collapse. Without the violent deaths of neutron stars, the universe would be a poorer place, lacking the ingredients that later form planets, technology, and even the chemistry of life. Every piece of gold on Earth, every atom of uranium buried deep in rocks, every trace of platinum that powers human machines, owes its existence to collapse. In a kilonova, when two neutron stars spiral together and merge, the ejected material can weigh more than the mass of the Earth, hurled into space at a significant fraction of the speed of light. Within that debris, nucleosynthesis forges heavy elements in quantities unimaginable. When astronomers observed the kilonova of 2017, they saw the spectral fingerprints of these elements forming in real time. Proof that collapse is not only destructive, but creative on a cosmic scale. The black holes born of collapse also reshape their surroundings long after the event itself. A newly formed black hole is rarely quiet. Matter from its environment spirals inward, forming an accretion disk that glows in X-rays. Magnetic fields twist and accelerate jets of plasma that shoot outward at near light speed, blasting through interstellar space. These jets are not merely dramatic. They inject energy into the surrounding gas, stirring it, heating it, and sometimes triggering the collapse of new clouds into stars. In this way, the death of one star can become the seed of many. Collapse does not simply mark an ending, it fuels the cycle of stellar birth. Multiply this across billions of stars and billions of years, and collapse becomes one of the hidden engines of galaxies. Stellar black holes, each only a few solar masses, are scattered throughout galaxies like embers from ancient fires. Each interacts with its environment, shaping the interstellar medium. Some consume their companions, flaring as X-ray binaries. Others roam alone, invisible, except for their gravitational tug. They are part of the unseen architecture of galaxies, the skeleton of gravity that holds stellar populations together. On even larger scales, collapse may have seeded the giants that dominate galactic centers. Supermassive black holes, weighing millions or billions of suns, rule the hearts of galaxies. How did they grow so large, so quickly, in the young universe only a few 100 million years after the Big Bang? One possibility is that they began as smaller seeds, remnants of collapsed neutron stars, and other stellar deaths in the first generation of stars. These seeds merged, accreted, and grew, becoming the gravitational beacons that now shape the orbits of stars and even govern the fate of galaxies. If this is true, then every collapse we see today is not just an isolated event. It is a glimpse into the process that built the universe's grandest structures. The permanence of collapse also echoes through cosmic time. A neutron star may survive for billions of years, slowly cooling, spinning down, and fading into obscurity. But a black hole, once formed, endures. Even Hawking radiation, that slow leak of energy predicted by quantum theory, operates on timescales far longer than the current age of the universe. The collapse of neutron stars into black holes ensures that gravity's monuments will outlast the galaxies themselves. When the stars have burned out and the universe grows dark, black holes will remain, silent guardians of everything gravity has claimed. But perhaps the greatest consequence of collapse is not physical, but philosophical. It shows us that endings are illusions. The death of a neutron star is not simply a disappearance. It is a transformation that enriches the cosmos. The elements forged in the violence of collapse become the building blocks of planets, oceans, and life. The black holes that replace stars become anchors for galaxies, shaping their growth and evolution. Collapse teaches us that gravity's victories are not barren defeats. They are fertile, writing new chapters in the story of the cosmos. As we move deeper into this chapter, we will explore these consequences in greater detail. We will follow the trail of heavy elements from neutron star mergers to Earth itself, trace the influence of black holes on galactic structure, and consider how collapse links survival and destruction in a seamless cycle. The collapse of a neutron star into a black hole is not only the end of one object, it is part of the beginning of everything. When neutron stars collapse, the echoes of their destruction reverberate far beyond the stars themselves. The most striking of these echoes is the creation of heavy elements, because the collapse of neutron stars, especially through mergers, produces conditions so extreme that new matter is forged. In a neutron star merger, the gravitational waves alone carry away more energy than all the stars in a galaxy radiate in the same moment. But the aftermath is equally profound. Matter is ripped from the stars' surfaces, hurled outward in jets and clouds, moving at nearly the speed of light. Within these expanding shells, the density of neutrons is so high that nuclei rapidly capture them, building heavier and heavier elements in what physicists call the rapid neutron capture process. This is the origin of gold, platinum, and uranium, elements too heavy to be made in ordinary stars. Without collapse, the periodic table, as we know it, would be incomplete. When astronomers observed the kilonova following GW 170817, the collision of two neutron stars detected in 2017, they saw these processes unfold directly. Spectra from the explosion showed the fingerprints of freshly minted heavy elements. In that one event, more gold may have been forged than exists in the entire Earth. Collapse is not only the end of a star, it is the beginning of chemistry that enables planets and life. Beyond forging elements, collapse also fuels the cycle of star birth. Black holes formed in these events can accrete surrounding gas, releasing jets of radiation that stir the interstellar medium. These jets inject turbulence and heat, sometimes compressing clouds enough to trigger the collapse of new stars. In this way, the death of neutron stars can seed the birth of others, linking endings and beginnings in a continuous cycle. Collapse also plays a role in cosmic architecture. Stellar black holes, scattered throughout galaxies, influence their surroundings over billions of years. They capture stars, distort orbits, and carve gravitational imprints into the galactic fabric. In dense stellar clusters, black holes born from neutron stars may merge repeatedly, climbing toward intermediate masses that could eventually grow into the supermassive black holes at galactic centers. These giants, weighing millions or billions of suns, may have begun as remnants of collapse in the universe's earliest epochs. On a human scale, the connection between collapse and existence is profound. The atoms of gold in jewelry, the uranium in Earth's crust, the rare elements in our machines all were born in the violent ends of neutron stars. The collapse of stars light years away and eons ago helped shape the matter we use daily. Without their sacrifice to gravity, our world would lack its richness. Collapse is not only an astronomical drama, it is part of our own history. The story is not finished with element creation. The black holes that remain after collapse endure, sculpting galaxies, outliving stars, and persisting into the deep future of the cosmos. In the next part, we will explore this endurance, following how black holes formed from collapse influence cosmic evolution, and how gravity's final authority guides the destiny of the universe itself. The collapse of neutron stars into black holes is not an isolated act of destruction. It is part of a chain of events that stretches across cosmic history, shaping the largest structures we see today. Galaxies themselves bear the imprint of these collapses. Each black hole born from a neutron star adds to the hidden mass that tugs at stars and gas, guiding their orbits and influencing the balance of entire systems. The scattered population of stellar black holes are invisible architects, unseen but undeniable in their gravitational pull. Over billions of years, collapses accumulate. In dense star clusters, black holes may encounter one another, merging again and again. These successive collisions can produce objects of intermediate mass, bridges between stellar black holes and the supermassive giants that anchor galaxies. It is possible that some of the monsters we see today at galactic centers, black holes weighing millions or billions of suns, trace their ancestry back to collapses of neutron stars in the universe's earliest generations of stars. If so, then the quiet death of a compact star is also the seed of galactic destiny. Collapse also shapes cosmic cycles in more subtle ways. The jets from accreting black holes inject radiation and particles into the interstellar medium, stirring clouds of gas that might otherwise remain dormant. Sometimes these blasts suppress star formation by blowing gas away. Other times, they compress clouds and spark new bursts of creation. The cycle of stellar birth and death is therefore regulated, in part, by the relics of collapse. Black holes act as both destroyers and midwives, halting stars in one region while igniting them in another. On the grandest scale, collapses feed into the chemical evolution of the universe. The periodic table itself is a record of stellar life and death. Hydrogen and helium came from the Big Bang. Carbon and oxygen came from ordinary stars. But the heaviest elements, gold, platinum, uranium, required the collapse of neutron stars. When you hold a piece of gold, you hold the ashes of a collapsed star. When planets formed in the young solar system, they carried within them the gifts of neutron star deaths long past. Even the building blocks of life, though lighter, exist in a universe whose diversity of elements depends on collapse. Without these violent deaths, Earth could never have been what it island. In the far future, long after stars have burned out, the legacy of collapse will persist. Black holes endure across epochs that dwarf the age of galaxies. Stellar black holes, though small compared to their supermassive cousins, will continue to exist for trillions of years, outlasting the suns and planets that orbit them. They are monuments to gravity's triumph, reminders that survival is temporary, but collapse is permanent. Even when Hawking radiation begins to erode them, that process unfolds so slowly that the universe will have aged beyond recognition before it makes a mark. Thus, collapse is not only about endings, it is about continuity, about how the universe recycles itself through destruction. Each neutron star that falls into a black hole contributes to the shaping of galaxies, the enrichment of matter, and the persistence of cosmic structures. Collapse teaches us that gravity is not simply a force of ruin, it is the author of transformation, linking the death of stars to the birth of worlds and the architecture of galaxies. As this chapter closes, we have traced the path from the intimate gold in a human hand to the infinite galaxies shaped by black holes. The collapse of neutron stars resonates on every scale. In the next chapter, we turn to the ultimate conclusion of this journey. When gravity wins, what remains? What does the triumph of collapse mean, not only for stars, but for the future of the cosmos itself? The story of neutron stars is the story of survival on a razor's edge. Born from the violent deaths of massive stars, they are held in balance by forces at the very limits of physics, gravity pulling inward with relentless strength, neutron degeneracy pressure pushing outward with quantum defiance. For a time, the balance holds. Neutron stars spin, they pulse, they shine faintly in X-rays. They endure for millions or billions of years. But gravity does not forget. It waits patiently. And when the moment comes, through accretion, through mergers, or through overmassive birth, it wins. The collapse of a neutron star is both sudden and final. One instant, there is a surface, a structure, a star. The next, there is only a horizon. The neutron star's individuality, its crust, its fields, its composition is erased. What remains is a black hole, an object of pure geometry. It is not matter in any familiar sense, but a region of space-time so warped that nothing escapes. In this moment, the star ceases to exist, and gravity claims victory. But gravity's victory is not destruction in the ordinary sense. It is creation. The collapse of neutron stars enriches the cosmos with heavy elements, seeds galaxies with black holes, and shapes the very architecture of the universe. Every ring of gold, every trace of uranium, every galaxy held in the grip of a central black hole, all are consequences of gravity's triumph. The universe we inhabit is not possible without collapse. The legacy of collapse reaches even further. Black holes endure across spans of time that dwarf the age of the stars. While suns flare and die, while galaxies collide and fade, black holes remain. They are monuments to permanence, structures written into space-time itself. Long after the last neutron star has cooled into silence, long after the last galaxy has dissolved into darkness, black holes will persist. Gravity, victorious, leaves behind objects that outlast all else. And yet, black holes are also mysteries. They erase information, conceal singularities, and challenge the foundations of physics. They show us not only the power of gravity, but the limits of our knowledge. In every collapse lies a question we cannot yet answer. What happens to the matter that falls in? Is information truly lost? What lies beyond the singularity? These are riddles gravity has hidden from us, daring us to look deeper. So the collapse of neutron stars is not simply a chapter in astrophysics. It is part of a larger narrative. It tells us that balance is fragile, that matter is finite, and that gravity is absolute. But it also tells us that endings are beginnings, that destruction creates, and that the universe is richer for every collapse. A neutron star teeters on the edge of survival, balanced for a time against the crushing weight of gravity. But when gravity finally wins, the star does not vanish into nothingness. It collapses into a black hole, an object more mysterious, more enduring, and more essential than the star it replaced. In this transformation, we see the deepest truth of the cosmos. Gravity is not only the destroyer of stars, it is the creator of worlds, the sculptor of galaxies, and the keeper of mysteries that may never be unlocked. When gravity wins, it is not the end of the story. It is the beginning of a deeper one. The triumph of gravity is written across every scale of the cosmos, from the collapse of a single neutron star to the structure of galaxies and the evolution of the universe itself. Gravity acts as both sculptor and executioner. It gathers dust into stars, stars into galaxies, galaxies into clusters, and clusters into the cosmic web. Yet it is also the force that tears stars apart, collapses them into black holes, and seals their secrets beyond horizons. To witness gravity's victories is to see both birth and death woven together, destruction and creation inseparable. Consider again the neutron star balanced on the edge of collapse. Its existence is an act of defiance, a temporary stand against gravity's inevitability. But this defiance is fragile. Add a fraction more mass, disturb the delicate equilibrium, and the collapse is triggered. The star implodes, the surface disappears, and a black hole takes its place. The event is catastrophic for the star, but for the universe, it is fertile. The collapse enriches the surrounding medium with heavy elements. It seeds the galaxy with a new black hole, and it contributes to the architecture of space-time itself. Gravity wins, but the universe grows from its victory. This duality is not limited to stars. On cosmic scales, the same principle holds. Supermassive black holes at the centers of galaxies both devour matter and regulate creation. Their jets and outbursts can strip galaxies of gas, halting star formation, or compress clouds to ignite it anew. They are destroyers, yet without them, galaxies might never have evolved as they did. In their paradoxical role, they embody gravity's essence, an unstoppable force that consumes, but in consuming, reshapes. The victory of gravity also speaks to time. Stars live for millions or billions of years, but black holes endure for epochs far longer. They persist while galaxies age and collide, while stars flicker out and planets freeze. Even Hawking radiation, the slow evaporation of black holes, unfolds over timescales so vast that they dwarf the current age of the universe. In this way, the collapse of a neutron star into a black hole is a transformation from the temporary into the eternal. The star's survival was fragile. The black hole's endurance is absolute. For us, creatures who measure time in decades and centuries, the permanence of gravity's victories is difficult to grasp. The collapse of a neutron star is not merely the end of one star, but the beginning of a structure that will outlast the galaxy it resides in. In collapsing, the star leaves behind something more enduring than itself, a monument to the inevitability of gravity. Yet victory does not mean clarity. The black hole conceals as much as it reveals. Its horizon erases individuality, its singularity defies description, and its radiation challenges our understanding of information. Gravity's triumph is not only physical, but intellectual. It leaves us humbled, staring at an object that embodies the limits of both matter and knowledge. The collapse teaches us that survival may be fleeting, but mystery is eternal. In the next part, we will close this journey, tying together the themes of balance, collapse, and legacy. We will look once more at the neutron star poised on the edge of survival, and at the black hole that waits when gravity finally wins. The journey of a neutron star is the journey of matter, tested to its absolute limits. From the moment of its birth, when a massive star detonates in a supernova, it begins its existence already marked by extremes. It carries within it the weight of one or two suns, but its diameter is no greater than a single earthly city. Its surface is so compact that a teaspoon of its matter would outweigh mountains. Time itself bends more slowly in its vicinity, and magnetic fields twist so violently they could strip the electrons from atoms thousands of kilometers away. Yet for all its strangeness, a neutron star is fragile in one profound sense. Its survival depends on balance. Gravity pulls inward with unrelenting strength, trying to crush it into nothing, while neutron degeneracy pressure pushes outward, the final defense offered by quantum mechanics. For millions or billions of years, this stalemate may endure. Pulsars beam across the cosmos, magnetars flare with sudden violence, and neutron stars cool slowly into silence. They are stubborn survivors, clinging to existence at the very threshold of physics. But the balance is not permanent. Inevitably, something tips the scales. Perhaps the neutron star was born already too massive, exceeding the Tolman-Oppenheimer-Volkoff limit at its creation. Perhaps it has a companion star feeding it matter, drip by drip, until the weight becomes unbearable. Or perhaps it collides with another neutron star in a spiraling merger that shakes the fabric of space-time itself. In every case, the result is the same. The limit is crossed. Resistance ends. Collapse begins. The collapse is catastrophic and brief. The star implodes inward, its surface racing toward its center, until the escape velocity at its shrinking boundary reaches the speed of light. At that instant, an event horizon forms. To the outside universe, the star freezes in time, its light stretched into invisibility. To the star itself, everything falls inward in a final rush. The individuality of the neutron star, its crust, its pulses, its exotic interior, is erased. What remains is a black hole, an object stripped to its essence. And yet, this victory of gravity is not an erasure into nothingness. It is a transformation. The collapse of neutron stars is the forge of heavy elements, scattering gold, platinum, uranium, and more into the cosmos. These elements become the foundations of planets, oceans, and life. Every human hand that clasps a ring of gold holds the memory of a collapsed star. Every atom of uranium buried deep within Earth's crust carries the story of a neutron star that surrendered to gravity. Collapse has written itself into the very matter of our world. The black holes that remain after collapse continue to shape the cosmos long after their birth. They carve orbits from starlight, bend the paths of galaxies, and anchor clusters of stars. They are monuments to permanence, persisting far beyond the lifespan of ordinary suns. Even when the universe has aged into darkness, when galaxies have faded and stars have burned out, black holes will endure. The transformation of neutron stars into black holes ensures that gravity leaves behind something eternal. Structures that persist into epochs longer than imagination can hold. But gravity's triumph also leaves us with mysteries. Black holes conceal information, swallow individuality, and defy the union of relativity and quantum theory. They remind us of what we do not yet know. They show us that physics, so powerful in explaining stars and galaxies, falters at the horizon of collapse. Each black hole is a question mark written into space-time, daring us to look deeper. This is the final lesson of neutron star collapse. Balance is temporary. Survival is fragile. Gravity waits patiently, and when it wins completely. Yet its victory is not sterile. It is fertile, seeding elements, shaping galaxies, and writing the future of the cosmos. From the ashes of neutron stars come the raw ingredients of worlds and the anchors of galaxies. From their collapse come both the silence of black holes and the richness of planets and life. And so we return to the image with which this journey began. A neutron star poised on the edge of survival, held in a precarious balance between crushing gravity and the final strength of quantum pressure. For a time it endures. For a time it resists. But when the balance breaks, when gravity finally wins, it does not vanish into nothingness. It transforms into something deeper, more mysterious, more eternal. It collapses into a black hole. The neutron star's story is over. Gravity's story continues. When gravity wins, it is not the end of the cosmos. It is the beginning of its next chapter.